Suppose we have a plane in space. Now there's infinitely many points on the plane, but there is only one direction that is orthogonal to the plane. So let's suppose, given a point x naught, y naught, z naught, and we have a normal vector n, let's just call it a, b, c, we would like to find an equation of this plane. Well, if I consider any other point on the plane, let's take x, y, z, then the vector between these 2 points must be orthogonal to the normal vector. In fact, every vector on the plane is orthogonal to the normal vector. So if we create this vector first, x minus x naught, y minus y naught, z minus z naught, then that vector and n have to be orthogonal. So if I said dotted with n, we would have to get the number 0. So if I replace n with simply this quantity here, this would give us the equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Now I would just distribute and gather terms, but this would give us a very simple representation of this particular plane. Now let's look and see, if we started with 3 points, how do we come up with the equation of a plane? Let's suppose we want to find an equation of the plane passing through these 3 points. We first need to create 2 vectors. Let's call those vectors PQ and PR. I do need to use the same point as the vertex. And then once I find these, since these 2 vectors live on the plane, their cross product will produce the normal vector. So PQ, 2 minus negative 1, 1 minus 2, 2 minus 4, and then PR, 4 minus negative 1, 3 minus 2, 1 minus 4. Now to take the cross product of these 2, the simplest way to do it is to simply stack the vectors as I have done. Then our normal vector, which is the cross product, will be 3 minus negative 2, negative 10 minus negative 9, and then 3 minus negative 5. That's it. It should never be more complicated than this. Now I just need to choose any of the 3 points, and I will create my vector x minus x naught, y minus y naught, z minus z naught. Dotted with n, we can go directly to the equation now. So let's take the first point here. So our equation would be 5 times x minus negative 1, negative 1 times y minus 2, 8 times z minus 4, all of this equal to 0. Now when I distribute, and I gather terms, I'll have 5x minus y plus 8z minus 25 equals 0. A simple check is that all 3 of these points must satisfy this equation. We know the area of a parallelogram. If I have the base, one of the legs, and the height, we know the area is simply a times h. But if I don't know the height, but I only know the angle between these 2, then just using SOHCAHTOA, this becomes a, b, sine theta, which should look very familiar, because the length of a cross product is the product of the individual lengths times the sine of theta. So now what I'd like to do is say, given these 3 points, P, Q, and R, let's suppose that in this case here, we simply change this. There's P, there's Q, there's R. These 3 points will uniquely determine both a triangle and a parallelogram, triangle if I go this way, in 3 dimensions. So if I said, what is the area of the parallelogram that these uniquely describe, all I have to do is find the length of this. Well, this would be 5 squared, negative 1 squared, 8 squared under the root, which would be root 90. Root 90 would be the area of the parallelogram determined by these 3. If I said, what's the area of the triangle determined by these 3, we would just take half of this quantity. It's a nice little added bonus. Okay?